Hello, my name is Pranav and welcome to my AESD project demo titled Crash Detection and Notification System. My teammates are Ganesh and Tejaswini. Let us now look at the project description. There are over 5 million car accidents in the US each year, with around 1% of them being fatal. Most of the injuries are usually associated to extreme deceleration. Response time to these accidents is very important in determining if the incident is fatal or not. Emergency services would also benefit if they could get accurate information about the accident, such as location, deceleration, and time of event. Our project aims to provide a proof of concept that gathers the following information and shares it to a cloud service, which can then relay a notification to emergency services. This attests to the fact that the sooner emergency information is related to concerned authorities, the better the response. Let us now look at the project block diagram. We are using the Beaglebone Black single board computer. We are interfacing two sensors, the MPU6050 accelerometer over the I2C bus and the MTK3339 GPS sensor over UART. We are writing a custom UART driver for the GPS sensor and using Linux's own I2C drivers for the accelerometer. Additionally, we are also interfacing the board with ThingSpeak, a cloud broker that hosts the crash information online, and we are developing a socket application that sends data to ThingSpeak. My contribution to this project was interfacing the accelerometer to the board and writing a user space application using Linux's I2C drivers to determine acceleration values. Additionally, I also wrote code to determine crash detection, which involved converting raw accelerometer data to useful G-force equivalent data to determine if a crash is detected or not. Additionally, I was also involved in writing code that performs the RESTful write API call to ThingSpeak, allowing for cloud-based notification system. This involved performing an API call via C from the Beaglebone Black to the ThingSpeak server. These are some of the challenges that I faced during this project. One of the main challenges was reliably determining if a crash has occurred from raw acceleration data, as the input data showed high variance. So scaling and normalizing this was absolutely necessary, and determining the right factors for this was pretty difficult. Another major issue was establishing connection to the ThingSpeak server using C, as obtaining known libraries with minimum number of inputs that were reliable were pretty difficult. These are some of the lessons that I learned during the course of this project. The first and most important lesson was setting up a cross-compiler development environment for the Beaglebone Black, complete with remote SSH access to the board to test application code. Since we were using a virtual QEMU device during the course, doing this with real hardware was very useful. Additionally, debugging I2C peripherals using Linux I2C tools was highly useful, as this also taught me of how Linux handles these peripherals and how you can manipulate these files to perform various operations with various I2C devices or read data off of different sensors from the bus. Let us now go into the project demo. This is our project setup. We have implemented our project on the Beaglebone Blackboard. We have interfaced two sensors, an accelerometer over the I2C bus and a GPS sensor over UART. We have also enabled SSH access to the board. Here is our executable. I shall run it now. We can see the acceleration data being read from the sensor. I shall now simulate a crash by inducing deceleration. We can see that the crash is detected, the GPS location being read, and the data being sent over to the ThingSpeak server. This is our ThingSpeak server. As we can see, the data is received over here with the GPS latitude and longitude. An alert mail is triggered immediately upon receiving new data, which we see here.